Thanks so much for having me. My name is Hortense Fong. I'm an assistant professor of marketing at Columbia University. Today, I'm going to be talking about how to think about designing models that are more explainable, and in particular, I'm really thinking AI models here. And so, specifically, I want to think about how to use theory, whether it's from the natural sciences, the social sciences, or perhaps thinking about managerial expertise, to design these AI models in order to maintain good predictive accuracy, but also get us explainability. So with that, let me get started. Okay. So it goes without saying that AI has made quite the splash. You have people like Google CEO saying AI is more important than fiery electricity. But if you're really giving credit here, fiery electricity and then AI. The reason that AI has made such a splash in many different areas is because it's been really good at making successful predictions, at generating very realistic or creative text, images, audio. So for example, we have GPT-4, which has performed extraordinarily well on many exams we think about as being very challenging. Bar exam, LSAT, GRE, SATs. And perhaps even more surprisingly, at least to me, we have AI models that have really done well in what we think of normally as creative areas. So AI's won photography contests, it's created music that's topped the charts. And so AI has done a really good job at many things, but this good performance doesn't come for free. And one of the costs is around explainability. So here we have these two dimensions. We have accuracy, explainability, and on the top left we see one set of models. These models I'm going to call traditional machine learning models. So they're models like linear regression, support vector machine, and the input into these models are handcrafted features. Because these features are handcrafted, we know exactly what they are, and so they're very easy to explain. The model is going to output something based on those inputs. But on the bottom right here, we have another set of models. Here I'm going to bucket it into AI or deep learning models. These models, they instead learn from the data itself features that are useful for classification or for generation. And it turns out that when you let the model learn these features, you get much better predictive performance. But this comes at the cost of explainability. Now you might ask, okay, but if we have good accuracy, isn't that enough? Why do we even care about explainability? So let me just get into a few reasons here. There are several. First, explainability enables trust. And managers need to have trust in predictions in order to be willing to deploy models at scale. In 2020, McKinsey conducted a survey that asked firms what they worried about when it came to using AI. And after cybersecurity and regulatory compliance, explainability was their greatest concern. Second, explainability gives us a sense as to whether a model can or cannot generalize to other data settings. And so I'll talk about this with a more concrete example shortly. Third, suppose you have a model that doesn't work really well, and then on top of that, it's also a black box. You're going to have a pretty hard time improving it. And finally, this is a topic I believe that's going to be covered later today, is that around ethics and fairness. So if you have these black box models, you might not have a sense of what data is being used for different decisions. You don't know if these decisions might be discriminatory in any way. And so if you have a model that's more explainable, you can better think about these issues around ethics and fairness. Now, let me just get into a more specific example, a more concrete example, just to solidify some of the ideas discussed previously. Here, I'm going to borrow from the Barrel et al. Paper. And in this paper, the researchers asked a very simple question. They asked, can we classify pickers of wolves versus huskies? These two animals, they look very similar. One is much more dangerous than the other, so it's an important classification problem to get correct. Well, these researchers, they were able to build a model with near 90% accuracy. But when they went to look at why, they didn't find that the model used themselves in the classification, but instead they used the background. So a white background led to this wolf classification, a green background led to the husky classification, and although this model is very accurate, clearly it's not generalizable, right? You can easily think of counterexamples in which you have this husky placing snow, so you can think the Alaskan Iditarod. So what explainability buys us here then is a sense of whether the model can or cannot learn features that would generalize to other settings. So if we go, in this example, we can think, we as humans, we know that the background information is not ultimately what distinguishes wolves from huskies. So maybe we can say to the model, okay, you can think about ignoring the background and instead just focusing on the animals. So then what I'm going to talk about today is I'm going to talk about how to incorporate theory into the design of a deep learning model in order to buy explainability, but without sacrificing the predictive performance that is associated with deep learning AI models. And in particular, I'm going to talk about a paper that does this to think about using a deep learning model to predict the emotion elicited by music. Now, the reason I'm interested in this is we know from behavioral sciences that emotion impacts consumer behavior all throughout the customer journey, and music is one of the key drivers of emotion. And in fact, the literature has often called music the language of emotion, and it has the ability to elicit a wide range of emotions. Now I'm going to show you two videos that raised money for the ASPCA. These two videos, they're the same in every way except in the background music, but the background music completely sets the emotional tone. So as you watch, take note of how you feel. The second one. Sorry, it's hard to watch a visual face. As you watch these two videos, you watch the first one, you felt positively energetic. As you watch the second one, you felt a bit more negative, lower energy. And these feelings, they perfectly map onto an emotion framework that was proposed by Russell back in 1980. The idea behind this framework is that all emotions can be mapped onto two underlying dimensions: valence, which measures how positive or negative you feel, and arousal, which measures how energetic we respond. I'm going to use this framework here in my model to characterize emotion because there's music theory and emotion theory that ties different features of music to these different emotion dimensions. Now, it makes sense that music is nearly ubiquitous in advertising, given that it's able to elicit so many emotions. A content analysis of ads found that 94% of ads use music, and that 75% of the time ads uses music. And so doing this, I'm going to think about how to use such a model that can predict emotion from music in the context of thinking about optimal ad insertion based on emotion. And here I'm thinking really about the context of YouTube mid-roll ads, and in the setting, there are two videos that we care about. One is the content video that you're going to YouTube to watch, and the second is the ad. So suppose we go to YouTube, we're watching Hamilton the musical. In Hamilton the musical, it varies in emotion over time. It begins high valence, low arousal, so an emotion like contentment. It quickly becomes high valence, high arousal, as he makes a name for himself. It ends on a tragic note, it ends low valence, low arousal. And ads often elicit an emotional response because they've shown emotion has proved to be more effective than, say, like truly informative ads in many settings. And we know from past literature that the interaction of the content emotion with the ad emotion impacts how effective the ad is. So here I'm going to ask a really simple question, which is just, where should I think about inserting this ad within a content video that varies in emotion over time? Now, given that music is designed to elicit the intended emotion in video content, here I'm going to abstract away from other elements of the video. I'm going to abstract away from the images and say text data, and just really focus on the music and use the emotion elicited by the music as a proxy for the emotion elicited by the video. And finally, in the context of YouTube, we've got billions of videos, millions of ads. If we want to think about this problem of optimal emotion-based ad insertion at scale, we're going to need a model to do this. And so, that's where we come in here. So my model can be easily summarized in this slide. I'm going to begin with the input data. This is going to be the raw music, and I'm going to convert it into these spectrogram images. So spectrograms, they're just a visualization of music. On one dimension, we've got the time, and then on the other dimension, we've got frequency. And the color just represents how much of a particular frequency is present at any time. So essentially, the spectrogram just reflects how the human ear works and breaks sound down into underlying frequencies and associated magnitudes. And then this spectrogram, this image, we can then input into a deep learning model, which has a particular architecture, convolutional neural network, which was really originally designed for computer vision, but has shown to be very effective in these settings, and so it's been applied to many different areas. So that's going to be our starting point here too. And then finally, the goal of the model is to predict for each music clip which emotion quadrant this music piece falls into. So we're going to discretize these valence and arousal dimensions into 4 quadrants. And so now let me get a little bit more into the model and what we're doing here in this paper in order to make this model more explainable. So here we have a picture of a CNN, a convolutional neural network, and this is a model that was designed with computer vision in mind, and so it was really motivated by how the human eye works. On the one side, we have the images that are input into the model, and then the output is a classification of what vehicle is in each image. And here you see that there are a lot of intermediate steps, and these intermediate steps, they're simple computations going on. There are a lot of them, which makes this model, you can think a black box because it's hard to understand what's going on. But computer scientists have made a lot of progress in understanding what these models do by going into each of these boxes. Now, what's going on here is there are the workhorse. What's doing the heavy lifting are these little square filters. So they're weights that are learned. They look at local pockets of information, so like square pixels and a square shape, and they just focus on the local area. This reflects how the human eye works, and then over time, this information is summarized until some features are extracted for a final classification. Now, if we think about using this model for thinking about classifying music emotion, we've got a problem because the human ear, well, we might have a problem in that the human ear doesn't work how the human eye works, right? So the human eye looks at local information, but the human ear, instead, at any given time, there's a distribution of frequencies that is like, hitting our, ear canals, and we're making sense of it. And so we might want to adjust this model to account for that. And so let me get a little bit into the music theory. This is going to be very high level. But the idea here is that for the sounds we hear, they're associated with different distributions over frequencies. There are certain sounds that sound really pleasant to us, or they sound very consonant for the musicians in the room. There are other sounds that sound very jarring or dissonant. So for example, octaves are something that sound really nice and pleasant to us. And the minor second sounds very jarring or dissonant to us. So the minor second, for example, is often used in horror movies. But what's important here is that it's the combination of all these frequencies that ultimately impact what we hear. And so what we're going to do is we're going to change those square filters to account for this information. And the reason I'm going to focus on consonance dissonance is because, okay, I better move faster. Okay, it's because ultimately these are perceptual features that relate to emotion. So consonant music is associated with positive valence and low arousal music, and dissonance is associated with low valence and high arousal music. But these ideas of consonance and dissonance, they ultimately relate to the physics of sound, in that when many frequencies overlap in a particular way, they sound very consonant to us. So we're going to design filters that capture frequency relationships that are associated with frequency. And so this black column here, this black and white column, will represent one example of a filter that I've designed. So in place of this square filters that capture local information, we're going to design this column filter. And the black portions of the filter are going to zero out portions of the image not associated with frequencies associated with consonants. And those visible portions are going to learn weights that will extract information useful for the classification of music. And what we find is that such a model is able to perform just as well as those vanilla convolutional neural network models that were first designed with computer vision in mind. But what we get in addition, the goal here was to talk about explainability. So let me get into that. And for that, we're going to borrow again from the computer vision literature, and there are these DAG-CAM heat maps that highlight what parts of an image lead to a certain classification based on some underlying model. So for example, suppose we have this image, and we want to know why it's classified as a sharp. If we take the GradCam heat map, the points of brightness highlight what parts of the image most greatly contribute to certain classification, to the sharp classification. And if we superimpose this heat map on the image, what we find is that it's the sharp teeth that are important in classification. And so this, this connects with our underlying intuition for how we would classify this image as sharp. So then for music, the question then is, well, what parts of music, what features lead to a certain classification? Why is this song here classified as being high valence, low arousal? So let's take a look. So here first on the top, I have this Mel spectrogram. This is the visualization of the music you just heard. And then on the bottom, I have a heat map that comes from the vanilla CNN model that's based on computer vision. And you can see that point of brightness highlight what parts of this song contributed to this high valence, low arousal classification. Looking at this image and looking at a broader set of images, it's really not clear what the model is learning to make this classification. But if instead we look at our model where we place more structure on the filter, we get something that we can understand and connects with our understanding of music and emotion theory. So on the right now, we have the same spectrogram on top, but the bottom is a heat map, a GradCam heat map that comes from the model where we've put some structure on the filter. And to understand this, I need to give you a little bit more information. What you heard there was a string instrument that changed notes that then became really spread out in sound. And what we know about string instruments is that they produce a very harmonic frequencies, or they produce a consonant sound. And consonance is associated with high valence, low arousal emotion. So then why was this song here classified as being high valence, low arousal? Well, the points of brightness highlight what parts of the song contributed to that classification. And we can see that these points of brightness exactly co-occur at the points of having those string instruments that produce the harmonic frequencies which sound constant to us. And if we look at these images over those 4 different quadrants, we see patterns that ultimately are in line with what we would expect from music and emotion theory. And one additional benefit of this model, this wasn't initially the intention here was to get something more explainable, but it turns out that this model that uses theory is also much more parsimonious. So this vanilla CNN model that uses the square filters, a very typical model we borrowed from another paper, and about 5 million parameters had to be estimated. But our theory-based deep learning model, which incorporated the music and motion theory, could reduce the number of parameters that need to be estimated down to 51,000. And so, if there are settings that where you might care about computation costs, which can be really high, or maybe there are other constraints, like if you're thinking about privacy concerns and you want things to be computed locally on someone's phone, and you worry about the amount of computation power something has, then maybe incorporating theory can reduce the size of these models. Now, let me quickly go back to what was the motivation of this, and this was this problem of YouTube mid-roll ads. So we have ads we have content that vary in emotion, we have ads that have a particular emotion, and we run a lab study that finds that ads that are similar in motion to the point of ad insertion are skipped less, and the brands are more likely to be recalled. So emotional similarity is what is effective. And then based on this lab experiment, we test whether different models would be able to predict what points of ad insertion should occur. So the ground truth is human tagging. If we use these traditional machine learning models, we're going to find points in the video that are more emotionally distant, and so those result in lower recall rates. But then the deep learning models, the convolutional neural networks, they do much better in that they can find points in the video more emotionally similar to the ad, and these result in higher recall rates. And our proposed model, using emotion, can do this in real time, at scale, and is explainable. And so what this tells us is emotion is an additional variable that we can think about for firms like YouTube, like Spotify, like Hulu, and thinking about this problem of ad insertion. Now, I want to finally close on this idea of, okay, what is theory? Theory is something that we think should hold in many different settings. And so we can take theory from the natural sciences. So in my paper, I talked about using the physics of sound and also theories from the social science. So thinking about the connection from music theory of the connection of different music features to different emotions. But also think about other areas, so human vision, inspired convolutional neural networks. We can think about how humans think about categorizing different things, so maybe prototype theory, and thinking about additional information that can be learned from models. And finally, managerial knowledge is definitely something that we can think about how to incorporate into different deep learning AI models to also increase explainability and buy more user trust. So with that, I'd be really grateful to get your thoughts and questions. Thank you for your time.